Hello, welcome to another lesson in Algebra 1. Today we are covering Module 1, Lesson 3. All right, so for your warm-up, you had a ramp is made of the shape of a right triangle. Using the dimensions described in the picture below, the ramp is length 10 feet from the top of the ramp to the bottom. So that's this way, the long side of the right triangle, which is the hypotenuse. And the horizontal width of the ramp is 9.25 feet. That is the long leg of this triangle because the height of the triangle definitely looks shorter. Okay. All right, so a ball is released at the top of the ramp and it takes 1.6 seconds to roll from the top of the ramp to the bottom. Find each answer below to the nearest point 1 foot per second. Okay, so we're looking for average speed, which is why it's in feet per second here. All right, so find the average speed of the ball over the 1.6 seconds. So we know that the ball traveled 10 feet during 1.6 seconds. So the distance the ball traveled, because we're looking for speed, is 10. And the time it took to travel that far was 1.6. So if we do 10 divided by 1.6 on our calculator, we can find the speed to the nearest tenth. So 10 divided by 1.6 will give us the speed of 6.3. It was 2.5, but I rounded up. And then this is feet per second. Okay, so that ball will travel 6.3 feet per second. And that makes about a good sense because it's 10 feet and it took more than a second. Okay, so then it should travel definitely less than 10 feet per second. All right, so find the average rate of horizontal change of the speed of the ball over the 1.6 seconds. So the horizontal change is this one. It went this far left to right, 9.25 feet. So this is going to be 9.25 over 1.6, which will be about, I forgot the squiggly equals on part A there, 9.25 divided by 1.6, 5.8 feet per second. Okay. Find the average rate of the vertical speed of the ball over the 1.6 seconds. So here's our problem. We don't actually know the vertical distance. So we need to find this out, and that's why in the hint it told us use the Pythagorean theorem. So the Pythagorean theorem, one more time, says the small leg A squared plus the other leg B squared, so the two small sides, which are A and B, the legs, should equal the hypotenuse squared. So we can fill in our parts here. We're just going to say that this small one is A, the other leg we know is 9.25, and we know the hypotenuse is 10. So 9.25 squared is 85.565, 5625, and I know 10 squared is 100. Okay, so we can solve this equation by subtracting 85.5625 to both sides. So 100 minus the 85 part will give us a squared is equal to 14.4375. Okay, and then we're going to square root that answer to find out what the length of A is. So A should be about 3.9 or 3.8. Okay, so the vertical distance was 3.8 feet, about. So if we divide that, 3.8 feet by 1.6, so 3.8 divided by 1.6 will give us the vertical speed, which will be about 2.4 feet per second. All right, so what relationship do you think will hold for the values of the three average speeds you found in parts A, B, and C? And our hint, once again, is to use the Pythagorean theorem. So we knew that this was the speed for the hypotenuse, and these were the speeds for the legs. Okay, leg 1 and leg 2. So let's see if that works for the Pythagorean theorem or about works, because we rounded all of these answers. So we want to check, is 2.4 squared plus 5.8 squared about equal to 6.3 squared? And we'll know if that Pythagorean theorem relationship holds for the speeds also. So this is 2.4 squared plus 5.8 squared will give you 39.4 is that going to be about equal to 6.3 squared? Let's see. This is 39.7. So there was some rounding errors in here because we rounded all three parts. And so it's not going to come out perfectly, but it looks like it does pretty much hold. So what relationship holds? The Pythagorean theorem holds for the speeds. Okay, so we could have used the Pythagorean theorem using this value and this value here, right here and here, to find the 2.4 without having to find the length of the triangle to begin with. All right, so that concludes our first page. Let's flip it over. All right, on the top of page 2, we have an example problem, just a reminder about some linear piecewise functions. So we have a story here. It says Daryl lives on the 3rd floor of his apartment building. His bike is locked up outside on the ground floor. At 3 p.m., he leaves to go run errands, but as he's walking down the stairs, he realizes he forgot his wallet. He goes back up the stairs to get it and then leaves again. And as he tries to unlock his bike, he realizes that he forgot his keys. One last time, he goes back up the stairs to get his keys. He then unlocks his bike and he is on his way at 3:10 p.m. So we want to make a sketch of what Daryl's doing along this, elevation versus time. So I went ahead and filled in blue here first. I knew my time was going to go in minutes because it's going from 3 to 3:10 and then onwards after he's done getting his bike. So I went by ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11, 12, 13. And then he lived on the 3rd floor of his apartment. So we call the ground floor elevation 0. And I think a floor of apartment's about 10 feet up. So he's 30 feet up. Okay. All right, so our job was to then figure out how to spread the story over that 10 minutes. So what I did was I had a half a minute of him getting ready to leave his apartment and walk to the stairs. And then I decided on 1 minute of walking down the stairs until he realized he forgot his wallet, and then 1 minute of hurrying back up the stairs. Okay. And then I had 0.5 seconds for him to go back to his apartment, so 30 seconds, 0.5 minutes, to find his wallet and then start back out again down the stairs. All right, so this time he made it all the way to the bottom. So I decided that was 2 minutes of walking towards the bottom. So then I went back and thought, well, that means that he should have got about halfway in 1 minute. And then he had to walk back up because as soon as he got down there to unlock his bike, he realized, uh-oh, I forgot my key. Went back up for 2.5 minutes. And then I gave him 30 seconds to go back to his apartment, get the key for his bike, and then 2 minutes to get back down the stairs. And then that last 3 minutes from 10 to 13, that's him staying at ground floor and riding off on his bike. All right, so there's a little holes in the story. There should be some places where you probably need him to hit landings or stay on the bottom for a couple seconds to realize that he didn't have his key, or take a couple seconds on a landing or a step to turn around and remember to get his wallet. But we kind of glossed over this in class and just said, oh, these should have a little extra lines there, but they're very hard to put a few seconds when we only go by minutes on our scale. Okay, so I connected them. I put in all these dots. So at 0, he was at 30 in his apartment. And then this was 1 minute right here. So halfway over, I put a red dot for him getting ready to go down the stairs. And then the next red dot was 1 minute from there. So, and I had him go, about halfway down the stairs. And then he had to go back up to the top in about the same time. And then back to his apartment. That's this red dot here. And then he made it all the way to the bottom of the stairs. That's that red dot. And then back up to the top. But I did 2.5 minutes this time because this is his second time walking back up the stairs. So he's a little bit tireder. And then he's able to make it back down the stairs in 2 minutes after spending another 30 seconds in his apartment. Okay. Then he unlocked his bike on the ground floor and rode off. All right, so if you should take a second and think about how I came up with this, write it on your paper, plot the red dots just like I did here, and then connect, and hopefully you have a ruler to help you connect with more straight lines here, because we're saying that he's changing his elevation at a constant rate the whole time. So my lines are a little bit crooked because I'm trying to write on the smartboard. All right, now at this point, you probably want to pause the video so you can see all this and get it all copied down correctly. Okay, number 2, we did an activity in class, and complete the table at the right as you make each fold with a piece of paper. So we passed out a piece of paper for every couple people, and then we started folding them. And if we had 0 folds, then of course we had 1 layer of the paper, okay? And then if we folded it 1 time, fold the paper in half, that means you have 2 layers. You can open back up and see the 2 layers. If you fold it a second time, like in half again, you fold it back out, you're gonna have 4 layers. 3 folds would give us 8, 4 folds would give us 16. At this point, the paper was getting pretty thick and it was hard to fold, but we could just realize that, hey, it looks like they're doubling, okay? So 1 fold gave us twice as much, 1 more fold gave us twice as much, another fold gave us twice as much, and so forth. Okay, so we could just follow our pattern, 32, 64, 128, 256, 512. So notice when you can no longer fold the paper, look for a pattern to continue the table. All right, so each time you made a fold, how does the number of layers increase? It becomes twice as much. As previous fold. Complete the statement below. Each time the paper was folded, the number of layers, well, another word for twice as much would be double. So this will be doubles, okay? All right, and then we made a scatter plot. Now here was our problem. We only did 9 folds, but the number of layers got to be more than 500. So I left the scale on the side here for the y-axis blank, and it should go 100, 200, 300, 400, 500. Okay, and then we plotted the points in green, and notice it didn't really get off the bottom of the line here until we got to about 5, and that's when we hit 32, so a little less than halfway. And then it started to really grow. So at 6 we have 64. That should be a little bit above, half of the first line. Okay, and then we had 128, so that's above the first line for 100, and then it's supposed to be about 1/4 of the way up. And then 256 was almost right in the middle of the second and third lines, and 512 was a little bit above that last line. Okay, so if we keep going, we can see what this graph looks like. So this curve we talked about in class is called an exponential curve. So this is an exponential function. It is growing exponentially, which in this case is doubling every time. Okay. Okay, on the third page here, we have when Mr. Elliott is bored during his drive home, he likes to pick a number and triple it over and over again. If Mr. Elliott picks the value of 1 to start with, then fill in the table for the first 5 values. So in class, we filled in up to here. Okay, so we knew 0 was 1, that's when I first started the game, and then the first time I tripled it, I got 3. The second time I tripled, I got 3 times 3, which was 9. The third time I tripled it, I got 9 times 3, which is 27. The fourth time I tripled it, I got 27 times 3 for 81. And the fifth time we tripled it, we got 81 times 3 for 243. Now, Mr. Elliott calculated after tripling the value 10 times, he got a number bigger than 1,000,000. Continue the table to see if he was correct. So then we added 6, 7, 8, 9, 10, and we tripled again to get 729. We tripled one more time to get 2187. And then the 8th time I tripled it, I got 6561. The 9th time I tripled it, I got 19,683. And the 10th time, only 59,000. So Mr. Elliott was incorrect. It was only about 60,000. Okay. But if you think about it, if I tripled that one more time, that'd be 180,000. And then one more time again would get us almost to 1,000,000. So if we triple it 3 more times, we would be over 1,000,000. So 13 times. All right, then afterwards, we took a second and we made a scatter plot again of this. And we had to choose an appropriate scale for our y-axis. And on the 10th one, we were at 59,000. So what I did was I went by 10,000. So we have 0, 10, 20, 30, 40, 50. And then on the 10th one was almost 60,000. So there was enough room to stick it up above there. So just like last time, our graph kind of hugs the x-axis for the beginning and then starts to grow and then really takes off in its growth. So we have another what is called exponential function. Starts off kind of low, hanging on, It all should be just barely above the x-axis there. I'm a little crooked on my line. And then it curves up really fast as the numbers start getting bigger. Tripling it makes it even bigger and bigger. Okay? So explain how counting the layers of the folded paper and tripling numbers are related. Both are exponential growth. Functions. They give the same curve graph, so they produce the same curved graph. Notice this curve, though, is different than our parabola one for our quadratic functions. It's not making a smiley face, it's kind of making an L that faces the wrong way, a capital L going backwards instead of forwards. Okay. Now, how are they different? Well, the difference is instead of doubling, we're tripling. So they're growing at a different rate. They are different because they grow a different rate. So one of them doubles, one of them triples. So this is double versus triple for the difference. Okay. All right, so the triple one's going to grow faster. All right. So notice by tripling a number starting at 1, we got all the way to 59,000. And if we look back to doubling a number starting at 1, we only got to about 1,000. So it grew a lot faster. So 1,024 if I did 10 of them, and here if I do 10, we have 59,000. So that's almost, what, 59 times as big. All right, let's flip it over and look at this last page. All right, on our last page, number 10 says, watch the following graphing story, and we have a link for it here. And it says, the video shows a bacterium doubling every second. However, the narrator says that the actual bacterium doubles every 20 minutes. Make a scatter plot of the number of bacteria there would be in the first 5 hours. So that's in first 300 minutes. 5 times 60, 60 minutes an hour, so 300 minutes. Of the breeding, be sure to pick a reasonable scale for the y-axis. Okay, you may find it easier to make the table first. So of course it's going to be easier to find the values we're going to plot before we try to make the graph for it. Okay. All right, so let's watch the video. So if you look at this video, it actually starts off with 2 bacteria. So that means they've already split once. And you can see one of these is about to split again. Okay, so let's keep a look at what's going on. Okay, so if we look at that again, she's saying one bacteria, if it produced split every 20 minutes, could actually make 5,000 billion bacteria. So it's probably going to be exponential growth. If we think about it, we're splitting each one in half every 20 minutes. So that's just like folding the paper, I think. So let's make a little table here and then see if we can plot these values. Okay, so I went ahead and made my table and I plotted the points. So for my table, I did time in minutes and then bacteria. So at the time 0, we had 1 bacteria. 20 minutes later, 2 bacteria. 40 minutes later, 4 bacteria. 60 minutes later, 8 bacteria. And all the way to 300 minutes, 32,768 bacteria. So remember, it was doubling the number of bacteria every 20 minutes. So that's why my time is going up by 20 each time. And then the bacteria is doubling. So 1 times 2 for 2, 2 times 2 for 4, 4 times 2 for 8, 8 times 2 for 16, times 2, 32, 64, so forth. And once again, we end up with exponential growth. Okay. So it hugs the x-axis for a while, barely growing. And then all of a sudden, it just takes off. Okay. So these first couple, if you look at my graph here, I'm going by the number of bacteria. Bacteria number. And I had to make my graph go up past 30,000. So I went by 3,300 for increments. So this will get me to 10,000. So 3,333. So about 1/3 of 10,000. Same with here, and then the same with here, okay? All right, so these first things, I mean, one of these increments here is 3,333 bacteria and a third. So, you know, none of these numbers in here even come anywhere close to 3,000. 512 is the first time we kind of get a little bit up, and that should only be 1/6 of the way up the graph. And mine's probably a little bit high right there, okay? So once again, you might want to pause the video, make sure you get the table and the graph. And notice our graph, once again, kind of looks like backwards capital L. It hugs the x-axis for a while, and then it grows up really fast. So kind of a curvy backwards capital L. So something like this, okay? All right, so all these functions, once again, are called exponential functions. And we have a general formula here for this. This is the starting number of whatever we began with. In most cases, we began with 1 here, okay? And then this B part tells us whether we're doubling or tripling or 1.5. That's the thing we're multiplying over and over again. So it looks like this. Like the first time we get the bacteria, it's just 1. The second time we get the bacteria, it's 1 times 2. The third time we get the bacteria, it's 1 times 2 times 2. And then the fourth time is 1 times 2 times 2 times 2. So you can see this is powers of 2. This is 2 to the first power, 2 to the second power, 2 to the third power, and that one is 2 to the 0 power. Okay? So this B part is what we're doing, doubling, tripling, or whatever, and then the X tells us how many times to do that. All right, so over the last 3 lessons, number 11, we've looked at linear, quadratic, and now exponential functions. How can we differentiate between the graphs of each one? All right, so linear is pretty easy to tell. That's the only non-curved one, right? All linear are going to be lines, and all lines are straight, okay? Exponential functions and quadratic functions, both of those curve. So quadratic functions, remember, looked kind of like a smiley face opening up or a frowny face. So that curve, that U-shaped curve that either opened upward or downward. So this is going to be, look for U-shaped curve. Now sometimes we have to get the other side of the U-shape, okay? So for us to tell, because a quadratic function, if I only show 1/2 of it, it looks a lot like an exponential function, okay? All right, so exponential function, okay? How can we tell that one? Well, an exponential function, we saw that it's kind of like a backwards L here, curved backwards L, which looks a lot like that half of the U one, so you have to be careful, okay? So look for a curved backwards L. Okay. All right, so that completes our lesson. You had to do a Module 1, Lesson 3 problem set, exercises 1 through 5. And I did give you a recording paper, but you need to read the questions and figure out what you record where. All right. So hopefully if you were out or you just didn't quite get it the first time, this will help you. And these will always be up on the class website. See you next time in class.